last us through the semester. Okay, so today we're going to continue our discussion of different types of priority queues. We're actually going to go beyond amortized analysis and see our first randomized data structures and talk about some tools for analyzing randomized data structures. I think the takeaway message that I want to get to, that I really want to stress, is that we are using priority queues kind of as a sandbox to kind of learn about ideas. All right, so by the end of today, we will have added like 5 things to this list of all the different types of priority queues we can implement. I don't expect you guys to have to implement leftist heaps in reality. Probably you'll never have to do that. But a lot of these priority queues are very useful in terms of illustrating high-level concepts that could be applicable in the design of other data structures and algorithms. So don't necessarily think, oh, I have to memorize how these specific priority queues work. Think, oh, okay, these are the interesting high-level design ideas illustrated by those data structures. Okay, so those are the higher-level ideas are what I want you to come away with. Yes?
Is there much reason in practice to use much beyond a binary heap for priority queues specifically?
So typically, 99% of the time, if someone uses a priority queue, they're using a binary heap in practice, or maybe a binary search tree, just whatever they happen to have a pre-built implementation of. If mergeability is important, then they're probably using some sort of more interesting heap idea. So, and all of these other heaps are very, very similar to each other, except, well, these two are kind of similar, and we're not really going to talk much about them. They're interesting, so look them up if you want. But the skew heap, the randomized mergeable heap, and the 3 or 4 others we're going to talk about, they're all maybe brothers or sisters, I guess, of each other. They're very close relatives. So calling them all completely different data structures makes it sound more intimidating than it is. It's really kind of it's variations on a theme. And you probably need to use one of those structures if mergeability is important. There are some applications where the ability to kind of meld or fuse 2 structures together can be important. A lot of times, though, if you just need a basic priority queue, the binary heap is lean and effective for that. It runs very fast. And you really can't, we're not going to beat these running times, the log n running times, like I mentioned before. One of these pretty much has to be log n. Getting one of these down to constant doesn't really help you in an amortized sense, because generally whatever goes in comes out on the other side, so the work per element is still log n. Depending on whether you call the insert or the remove min the log n, it's still log n. And you can't beat that because there's an inherent lower bound on sorting that basically means if both of these were better than log n, you could sort faster than n log n, which is kind of a no-no, which we'll get to that in about one lecture and talk about everything you ever wanted to know about sorting. So today we're going to talk about lots of different things, but kind of just touch on interesting high-level design ideas using priority queues as kind of the medium for articulating that. Okay. All right, so last time we talked about skew heaps and we talked about binary heaps. I think we ended with heap sort. So this is kind of another nice feature of binary heaps, is they give you kind of a free sorting algorithm. Remember, the cool and surprising thing about binary heaps is that you can build them in linear time, kind of in a bottom-up fashion, where you sift everything down, moving up in the heap instead of sifting everything up. This is interesting and cool. The sad thing is that in the end, it really doesn't help. Because yes, you can build a heap out of n things and order n time, but then you typically still have to remove the things from the heap. And removal takes log n time per element. So at the end of the day, you're still talking about kind of n log n for heap sort, even though you can kind of build a heap in linear time. This is kind of akin to being able to insert in constant amortized time. So that's cool. You can get the elements into a heap fast, but taking them out is a little bit slower. It takes log n time per element to pull things out of a heap. Okay. So let's go back to kind of our original idea with the skew heap and talk about these slightly more versatile heaps, these mergeable heaps. So we're going to depart from this rigid structure the binary heap had. Remember, the binary heap had every single row filled in completely, which as a plus meant that you could represent the binary heap in an array. You have this level order encoding that lets you encode what would normally be a tree in nothing more than just a regular old array, which is really nice. It makes the binary heap very easy and lightweight to implement. when we move to kind of general tree shapes, then we have to treat these things like trees. Each node is kind of an individually allocated block of memory. It has pointers to parents and children and all that. So implementing these things gets a little bit more interesting. You have pointers to deal with and whatnot. But let's go back to this picture of just a generic binary tree that's heap ordered. So that, it satisfies the heap property. The parent is always less than or equal to the child, so the minimum is always at the root. And you don't have to have balance, right? Any shape is okay, all right? There are a whole bunch of heaps based on this idea. The binary heap is kind of an exception. It has a very special, kind of rigid, almost complete shape. These things are a little more flexible. They can accommodate any shaped tree, I guess. And we talked about how skew heaps work. And the key thing with this is almost all of the heaps based on that more flexible idea, they're all based on merging, right? Because if you can merge two heaps quickly, you can pretty much do anything quickly, right? You can insert by just merging your heap with a new one element heap. You can remove the minimum by taking the root out and then merging its two subtrees back together. You can actually implement all of the other operations using combinations of things. So for decrease key and increase key, to change the key of somebody, typically you don't want to change somebody's key if they're deeply within the structure, because that could violate the heap property. So usually what you just do is delete someone and just reinsert them with a new key if you're going to change somebody's key. So all you have to do is handle deletion. And to delete somebody, how do you delete a node in a tree? If your tree supports merging, how do you delete somebody? Like I delete the 5, what do I replace the 5 with?
Smaller child.
I just replace it with the merge of its two children, right? So that's a very clean way that when we learn about binary search trees, we'll learn about, there's an operation called join. It takes two binary search trees and merges them into one. So to delete from a binary search tree, you just replace a node with the join of its two children. Okay, so there's a very clean way to delete from a structure that supports merging, okay? There are a couple of issues with deleting that we'll talk about later on. Deleting is kind of the interesting operation. But in general, to delete someone, you'd replace them with the merge of the two children. Okay? So once you've got merge, you've got everything. So all we really need to figure out how to do is merge. And then all the other operations just kind of naturally fall out from that. So how do you merge? All right? We talked about very briefly merge sort, which as a part of merge sort, there's this kind of building block of how do you merge two sorted arrays. So let's go back to that briefly, this idea of merging arrays together. This is a really, really common procedure that you see a lot. You've got two sorted arrays, and you want to merge them into one sorted array. It's a very easy thing to do, and you can do this in linear time in the number of total elements. But there's a couple of different outlooks on this merging process. So usually when you learn about merge sort, the way that you are taught how to merge is kind of this iterative approach where you have kind of two indices or two pointers that kind of monotonically scan down these two arrays. Initially they point to the two first elements, and you take whichever one is smaller and move him to the, to the output array, and then that pointer advances. And then again, you take whichever one is smaller, and that goes into the next slot, and his pointer advances. So you're kind of just iterating, almost like with a for loop or a while loop, with these two pointers that kind of monotonically trace down the two arrays, and you're always taking the min of the two things and putting it next, all right? That's kind of a loop-based way of thinking about merging, all right? There's another, in my mind, cleaner way to think about the merging process, which I appreciate it and I want to kind of condition you to think more along these lines recursively and inductively. Here's a different way to think about the exact same process, all right? Basically, all you need to do is get the right first element and then just delegate the rest to recursion, right? So look at the two leading elements. Whichever one is smaller has to be the first element of the merged array. Once you've done that, once you've taken whichever of those two elements should be first, you kind of remove that element from consideration. What's left? What's left is another instance of the merging problem. It's just smaller. It involves n-1 total elements instead of n total elements. And how do you solve that problem? I'm just going to make a recursive call to merge, right? So basically, get one element right, and then just recursion, you can handle the rest of the problem. I trust you, right? That's the way you want to think about what recursion is good for. Anytime you can effectively take a large problem and hack off a piece of it and reduce it down to a smaller problem that has the exact same structure as the original, recursion will work, right? Recursion will solve that smaller problem. You just recurse on it, okay? If you think about what the recursion is going to do, it's going to do exactly what the iterative approach had done. And if you implement it incorrectly, it'll actually blow up the stack and crash, which is another. So in practice, implementing things like this is sometimes a little bit tricky because in practice, there's actually like a recursion stack that has limited size. So you may actually want to implement it iteratively instead of recursively. But thinking about the problem, I like to kind of think about it from this recursive standpoint. There are lots and lots of algorithms where you just have to kind of get one piece of the solution right, and everything else you can just call yourself recursively to complete the solution. Later on, we're going to talk about a technique called divide and conquer, where you effectively can take a big problem and kind of cut it up into pieces and recursively solve the pieces. It's similar in terms of the outlook. But so there are two ways to think about merging, kind of the iterative and the recursive outlook. Both of them are really the same process viewed two different ways. They both take linear time. There's no difference in running time. Okay? But this comes into play because we want to merge two heaps now, not two arrays. And it turns out there are two ways you can think about the process of merging two heaps together. You can think about it kind of recursively, which we did last time, or iteratively. Let's look at this is the picture that we looked at last time, where we are kind of thinking about the merging process recursively, right? You want to take two heaps and merge them together. One of them has the smaller root, so you kind of think about its root has to be the root of the merged heap, and you're taking the other heap, the one with the bigger root, and kind of merging it into the one with the smaller root. And so you basically, it's a very, very simple idea. You choose the left or the right subtrees and you recursively merge with one of them, right? So maybe I choose the left subtree, so I replace my left subtree with the result of recursively merging my left subtree with this guy. And so the left subtree gets bigger because it swallows up this new heap. And that process involves a lot of complicated stuff, but you typically, mentally, you don't go there. You don't think about it. You stop at one level of recursion, and remember, trust recursion to do what it's supposed to do. So I tell recursion to merge this heap with that heap. That is a smaller version of the original problem, so recursion will just do that, all right? This is important when you guys take discrete math and whatnot. One of the proof techniques that is drilled into your head is induction, right? What's the core essence of the idea of mathematical induction as a proof technique?
It's like solve for a preliminary case and a boundary case, and then just the rest of it you can kind of induce that the rest of the problem is solved.
What's kind of the key high level thing behind induction that's important that is kind of related to what I just talked about with our recursive outlook here in terms of trusting recursion and not having to unwind the recursion, beyond the first level, right? Mathematical induction basically says if you're trying to prove that something is true for a large value of n, you can assume that it's true for smaller values of n, all right? As long as it's true for some base cases. Kind of in terms of algorithms and data structures, if I'm trying to assume, if I want to prove that my algorithm correctly merges two heaps of size n combined, I can just assume by induction that it correctly merges any set of heaps of combined smaller size, all right? So induction is kind of the underlying principle here. It basically, and if you're trying to kind of give a formal proof that this is correct, you would basically phrase your proof as a proof by induction, because you can say, in order to prove that merging two heaps of combined size n is correct, I can assume by induction that my algorithm will correctly merge two heaps of combined size anything smaller than n. So anytime you can reduce your problem to something smaller, you can just assume by induction that recursion will solve it correctly. Very cool, all right? So you really can trust recursion to do the right thing. So recursion and induction kind of are two sides of the same coin. All right, so this was our recursive outlook. Now I'm going to do what I told you not to do. Let's think through the recursion, right? What actually happens as part of this recursive process where you merge H2 with your left subtree, and that involves a smaller recursive problem where you're merging two heaps, and then that spawns a smaller recursive problem involving merging two heaps. That sounds very mentally confusing to think through many levels of the recursion, but actually there is a simple way to think about that. And it kind of is like, when you're merging two sequences, it's kind of the analog of the iterative outlook on how to do things. So here's another way to merge two heaps. what you do is in both of the heaps that you want to merge, you pick what's called a null path. It's a path from the root down to an empty space, a null at the bottom of the heap. So I put these little yellow circles to indicate kind of null pointers. So if you have a path that walks from the root all the way down to an empty space, a null at the bottom of the tree, so it falls off the bottom of the tree here, and I pick a null path here, what are these null paths? They are, if nothing else, they are sorted sequences, right? I've got a sorted sequence here and a sorted sequence here, thanks to the heap property. And what do I do with two sorted sequences? I want to merge them, right? That's what we just, so what happens if I, and how do you merge two sorted sequences? Well, one way to do it is recursively, right? Just get the first element correct. Look at the leading two elements, choose whichever one is smaller, make that the first element of the merge sequence, and then just let recursion mop up everything else. That's kind of what we just did. That was the recursive outlook on merging these two heaps. What's more of the iterative outlook? You start a pointer here and a pointer here, and you take whichever one's smaller and kind of put it first in the merged heap, and then its pointer advances. So then this pointer would advance to the 5. All right, so now our pointers are here and here. And you take whichever one is smaller and kind of put it next. And so you're basically taking two pointers and they're monotonically tracking down these two null paths kind of in lockstep, always taking whichever one is smaller and putting it next. And when you do that, it basically kind of like, I like to think of it as just kind of closing a zipper. It kind of just zips the two heaps together, and you actually get a merge of the two heaps. And the process is really the exact same process as the recursive process. It's just looking at it a different way. All right, so, and this way of looking at it actually gives us more insight sometimes into the running times of operations and how to design our data structures. So sometimes looking at something recursively versus iteratively can just open up new ideas in our mind for how to do things. So you can kind of see in the merged heap, you can see the remnants of both of the null paths are still there. You just kind of like interleave them together in the right way. So that the merge of the two null paths is now one big sorted sequence. So this really does generalize merging arrays. It's just merging kind of the vertical paths in two heaps together. And it really is just one process. We're just thinking about it two different ways. Kind of an iterative way where you kind of walk down two null paths in tandem, kind of like zipping them together, versus a recursive process where you only look at the first step and you put the first thing in place and then just let recursion, you call recursion on everything else, but what recursion does is it ends up walking down the null paths, just the way you would have done it iteratively. Okay. So given this kind of different alternative outlook on merging, what does this suggest in terms of efficiency? If you want to merge two heaps together, which null paths should you choose to merge along? Because a heap can have many, many null paths. What sort of null paths should we choose? Short ones, right? So if you choose short null paths, the merge process runs fast. If you choose an ill-advised long null path, like I'm going to go all the way down through the 10 or whatever, that's going to take longer in the merge process. So the hope is that you choose short null paths. The skew heap does this in a really weird way by having these like preferred child pointers that kind of flip back and forth, and it amortizes out well, but it's kind of hard to think about. Now that we kind of have this picture in front of us and we just know that we need short null paths, how do you find a short null path in a tree? Right? I gave you here's a tree. What sort of mechanisms can I try and put in place that allow me to find pretty easily a short null path?
Like subtree sizes, like augmenting?
Yeah. So let's do that. So basically, the time it takes to merge two heaps is proportional to the combined lengths of the two null paths we choose. And it turns out every end node binary tree has a short null path. Every end node binary tree has a null path of length log n. Why is that?
They can't all be greater than log n.
Yeah, if they're all greater than log n, that means kind of the height of the tree. The tree is like completely filled in all the way to a depth of log n. That doesn't actually make sense because how many nodes would there be on the log n level of a tree? You double the number of nodes every level down in the tree. So you have 1 node, then 2 nodes, then 4 nodes, then 8 nodes, and so on. How many nodes would you have if you go log n levels down and it's completely filled in all the way down to that point? You'd have 2 to the power of log n nodes. Another name for this is n. This is actually a nice property of logs. 2 to the log of something kind of cancels, right? And you just get that something. Another nice property that's kind of cool is if you have like a to the log b, you can swap a and b. That's b to the log a. And actually that helps you prove this easily, right? Because you swap the n and the 2, and you get n to the log base 2 of 2, which is 1. So knowing logs is helpful. Another way to think about this, if I'm the root node, I have two child subtrees. One of them is smaller than the other. So if I step to that child subtree that's smaller, what's happened to the size of my tree? I started in a tree of size n. If I step to my smaller subtree, what's my new tree size?
Less than
half n, because I've lost half of my mass by stepping to the smaller child. If I keep doing that, every step I take, my effective subtree size shrinks by at least a factor of 2. All right, so you can only do that log n times before you get down to nothing. Right, so that's another way to kind of argue this sort of idea. That sort of argument is done a lot in data structures and trees. So there are short null paths. We just have to find them. And what Stephen suggested was you can just kind of turn that idea into a data structure, right? If you want to find a short null path, you always want to step to your child that's smaller. So why not augment every node with its subtree size? So I'm going to attach an extra data field to every node that is the size, the number of nodes in its subtree. So the root has, tells me the total tree size, and every node has an augmentation attached to it that is the subtree size. And this is a big high-level concept. Lots of times we do this with data structures. We augment them with extra information, right? And that extra information helps us solve problems more efficiently, because now I can find a short null path. Which way do I step? Well, I look at the subtree sizes of my 2 children, and I step to the one that has the smaller subtree size. And I know that process will give me a null path of length log n. So if I have the tree augmented thusly, I can find short null paths, I can merge in log n time, and I'm done, right? Yeah, it kind of, there's got to be some drawback, right? Why don't we just augment everything with extra information? What's the downside of augmenting things with extra information?
updating it.
Yeah, you have to keep it up to date. So you have to think anything that changes the structure of your tree, now that those update operations have to be able to update your augmented information. So queries get faster and updates get slower, I guess, if you augment a data structure. But sometimes that's a trade-off you're willing to make. What's the only way we update these trees? There's only one operation we're ever doing, which is merge. Everything else is expressed in terms of merge. So if we can update these numbers during merging, we're okay, right? Because everything else just call merge. And it turns out that, yes, you can do that. So if you have 2 size augmented heaps, then you merge them together. Which nodes in the merged structure might need to be updated? All right. I've underlined them, and it's pretty easy to see. The only nodes whose sizes change are the ones along the merge of the null path, right? So if you merged along 2 null paths that were themselves short, length log n and length log n, this combined null path is going to have length order log n, and only that null path is going to have to be updated. How do you actually do that update? How do I actually change these numbers after the merge? Like, say I do the merge, and then I know that I need to go and update these numbers. How do I do that effectively?
Just add its 2 children.
Yeah, I can just kind of start at the bottom and walk back up the combined merged path, and I can update these numbers as I go up the tree, because each number is really easy to compute once I've computed correctly its 2 children, right? This guy's size is the sum of his 2 children's sizes plus 1 for himself. So usually, if you augment a tree and you do something to the tree, there's an update step where you usually you have to walk up the tree from wherever you've made updates and kind of recompute the information as you go. And as long as you can recompute the augmented information on a node from just the augmented information on the 2 children of the node, you're usually okay, because you can walk back up the tree and recompute everything in just order log n time. So this doesn't change the order log n running time of merge. It just adds another order log n step of updates. In fact, this is even cleaner in the recursive viewpoint, right? If you think about merging things recursively, then what do I do? How do I now imagine that I want to change the recursive picture here to work with size augmentation. So every single node has a little augmented value on it that's the subtree size. So where does that show up in this recursive picture? Well, I have to choose between my left and my right subtree to recursively merge with. So which one do I choose? The smaller, the one with the smaller augmentation. So recursively, I will take this, the child of the smaller size and merge this heap into it, and that will give me a new tree. What's going to be sitting at the root of that tree? So
The new subtree
size.
size, yeah.
And why is that magically going to happen? Induction, right? You can just trust induction not only to do the merge, but also to update the augmented values in the merge subtree, right? So just trust recursion to do everything it needs to do. So the merge subtree, its root is going to reflect the correct merge size of everything, and this root's correct. We didn't touch this subtree, so then all we need to do in the recursive outlook is just update the root, right? So it's an even easier picture, kind of. Same thing is happening as would have happened in the iterative case. It's just happening in like a different mental order, I guess. So here, you still have to keep the sizes up to date, but all you have to do is update the root after all the recursion happens. Yeah.
If you augment the nodes with subtree size, you're guaranteed to get log n.
Guaranteed log n, yeah.
But not guaranteed to get the best null path.
That is, oh, like the absolute best null path. I agree.
Yeah.
Right.
Yeah.
You could have one of your children could be really, really big, but maybe he has a null child. And so you could have like a really short null path just hanging out there as part of the larger subtree that you'd miss. So you're guaranteed to get an order log n, but not the absolute minimum.
Okay.
Right? So what if you wanted the absolute minimum? You know, Corey is very demanding, guys, so he won't take log n for an answer. He wants the best null path. And by doing that, you're going to get at least log n, maybe better. Is there a different way we could have augmented that would guarantee finding the best null path?
The shortest null path length from that.
Yeah, so instead of kind of using size, which is a little more one step removed from like this idea of null path length, why not just augment every node with the length of the shortest null path for that node? So these guys would have ones. Well, let me see. There we go. Augmenting with null path lengths. Thank you, Corey, for the excellent segue there. So every node is just augmented with the length of the shortest null path to get to the bottom of the tree, right? So, you know, this guy's augmented with the 2 because there's a 2-step null path leading from him down to an empty space. And this is even more direct because if you want to find the shortest null path, if my number here is x, then one of my 2 children has to have x minus 1, right? That just has to be the case. And so you step to whichever child is 1 less than you, and then keep doing that, and eventually you'll discover not only the shortest possible null path, but you know that null path will have length at most order log n. Okay. I'm getting some kind of all of a sudden I get a vibe that's like, is everyone okay with that, or okay, cool. If I merge 2 of these trees together and have to update these numbers, are these easy to update? Remember, all I need to do is be able to update the number of a node based on the numbers on its 2 children. If I can do that, I can walk back up the tree and update along the merged path, or recursively, I can just update the root after the recursion happens. How do I update the number on a node based on the numbers on its 2 children?
Just add 1.
And its children.
Take them in and add 1.
Yeah.
So that's easy. So I can use this augmentation as well as the size augmentation, and everything works. The nice thing here is this is giving me worst case running times. Order log n worst case. You know, take that skew heap in your log n amortized time. You know, this is always order log n versus the skew heap is log n amortized. So it potentially could have some slow operations and some fast, but over a sequence, it averages out to log n. But the skew heap is arguably cooler, right? It's got the coolness factor going on. These are kind of more old school data structures that, that yes, they work fast. There is actually an issue with these. Suppose we have size augmented heaps, and this is why I was saying that like they're all siblings in the same family, right? There's only kind of one idea here, but it's just how do you find your short null paths? Like the skew heap kind of does this alternating back and forth thing. You've got null path augmented, you've got size augmented. There's a lot of ways we can choose these short null paths, and they give us variations on a theme. There is one operation though that is problematic. What operation could potentially be an issue if we have to start augmenting our data structure and maintaining those augmentations?
Oh, deleting?
Deletion.
Yeah. Remember, insert and remove min are not a problem. But delete, if you want to do like an increase key or a decrease key, then that needs delete because you delete someone and reinsert with a new value. So we kind of need, deletion is the only other operation that we need to think about, and we might need to delete someone really deep in the structure. All right? If you delete someone really deep in the structure, what has to, suppose you've augmented with subtree sizes, you know. If you delete someone really deep in the structure, here's a picture. You know, I delete element E, for example, or I take out a subtree. You know, for example, maybe I delete E, which means I take out E subtree and join the two kids together and splice that back in. So I basically replace E with the merge of its two children. So effectively, the subtree rooted at E has lost 1 unit of size, right? That loss of 1 unit of size, you know, if I kind of remove, you know, 1 unit of element or P elements, that has to be reflected in the subtree sizes of everyone all the way up to the root from that guy. So if I like remove P elements or 1 element from really deep in the tree, there's a very long path potentially leading up to the root that I have to subtract from in terms of updating my subtree sizes. And since I'm not insisting that these structures are balanced, I could be in trouble here. If I delete from a really, really deep subtree, then I'd have to update subtree sizes on a very, very long path up to the root to keep them up to date, right? So it seems like
So would that be like order n?
this could be order n in the worst case, because that path could be everything, you know, in the very worst case, you've got like a tree that doesn't even look like a tree, it just looks like a long sorted path. And you delete the lowest guy, you have to walk all the way up to a path and subtract 1 from the subtree sizes of everybody. So we just broke our data structure. Let's fix it, right? How do we deal with this issue? This is the problem with augmenting a data structure, right? Now you have to keep the augmentations up to date, and here's a case where it's expensive to keep the augmentations up to date. So what do we do to fix this? I think we mentioned the possibility last time.
Oh, the tombstones?
Yeah, let's not actually delete someone. Let's use lazy deletion. If I tell you to delete element E, yeah, trust me, I deleted him. I just kind of like put a little mark saying, yeah, he's deleted. And then, so if you delete someone and then reinsert them, you don't actually delete them, you just reinsert them. So you actually, you have this dead element floating around as well as the new live copy that was the updated copy, if you did like an insert or an increase key or decrease key. So you have elements that are flagged with little tombstones that are kind of really deceased elements. And the nice thing is that doesn't change subtree sizes or null path lengths, so you don't actually have to update your augmented information. That creates other problems though, right? Because there was a comment last time that your data structure could fill up with dead elements and you'd be wasting space. But if you ever fill up with like, say, more than 50% dead elements, you can just overcharge the deletions by a little bit so that you can pay to rebuild your data structure at that point to clean out and garbage collect out all the dead elements. So in an amortized sense, you can make sure that the data structure never has more than like some constant fraction worth of dead elements. That's kind of free in an amortized sense. We also, if you have dead elements floating around and you remove the minimum from your heap, the minimum could be a dead element, and that's bad. However, if you remove the minimum and it's a dead element, you just throw it out, do another remove min, oh, that's a dead element, and you just keep doing successive remove mins to kind of clean out the dead elements at the top of the structure until you finally remove a good element, and that's what you return. So remove min gets slower, but you can pay for the removal of the dead element in advance. When you say delete this guy, just charge yourself the log n at the point in time of the deletion that you would be paying to delete him with remove min. So you're basically taking that expensive running time for remove min and charging it earlier when you told yourself to delete that element. So from an amortized perspective, everything works out fine. We're just doing lazy deletion. On the downside, now our data structure is an amortized data structure instead of a worst case data structure. So, you know, all the wonderful, you know, claims about order log n worst case performance, they go out the window if we need to do this sort of lazy deletion, because now our data structure has amortized performance, but still log n for everything. Right? So we can fix this at the expense of adding amortized quantifiers to things. Okay. Here's a data structure structure that I really kind of don't like. So I'm mentioning it kind of more for historical reasons because somehow this data structure, it's out there and people know about it, and some people like it, they think it's cool. It's not cool. It's a clunky way of looking at what we've already done, all right? That really doesn't give you, a lot of times in a class, people will teach like just this and none of the other surrounding context. And I think you miss out on a lot if you just see this idea because it looks very random and arbitrary. The leftist heap is basically, it is a null path augmented heap, just like we just did. It's just for every node, you swap the children to make sure that the left guy is the one with the longer null path, and the right guy has the shorter null path. So it is really nothing different from a null path augmented heap. It's just every node orders its two children so that the right guy is the one you want to move to that has the shorter null path. And so that's kind of nice because it means that if you want to choose a short null path, you just walk down the right side of the tree, walk down the right spine of the tree, and that always has length order log n, all right? So if you want to merge two heaps together, the merging picture, maybe the merging picture looks a little simpler. This is basically that same merging picture we had before. Just instead of having the null paths do like zigzags down the tree and merging them and getting a zigzagging looking thing, now you're merging the right spines together, which are nice. They're nice, linear looking, right? So maybe the merge picture looks prettier, but it's essentially the exact same merge picture we had from before, right? To merge two trees together, you merge them along their right spines. Okay? The trouble is, after you do the merge, this tree may not be leftist in the sense that the nodes, that was an interesting one. The nodes along the right spine of the merged tree, they may not have this leftist property, right, where the right side is the way to go. However, you still have augmented values on these nodes that are the null path links, and you can swap the children if that condition is violated. So after you merge, you basically walk back up the right spine of the merged tree, and you swap anyone that you need to swap to restore this leftist invariant, okay? So this is the leftist tree. It really is no different whatsoever than the null path augmented tree. It's just every node pretends that the child with the shortest null path is the right child. That's the only difference. It's just kind of this convention that your right child is the better one, all right? It makes the merging picture maybe look a little bit simpler. But it really is from a high level perspective, it's no different than the null path idea. And I think it's important to go at this thing from the, starting from the null path perspective, because that's really the insight and the intuition that you need. If you just learn about the leftist heap, you kind of learn about this without surrounding context, I think. And a lot of people think this is a cool data structure, but it's kind of just, it's another way of looking at what I think is a more abstract idea. Does this make sense, kind of the leftist heap idea? So if someone kind of tries to sell you on a leftist heap, that's a good idea. They know their data structures, but there's kind of a bigger concept. This is just a special example of. The interesting thing is, remember when I talked about skew heaps way back when, last lecture? Gosh, there's a lot of slides here. When I talked about the skew heap merge, remember with skew heaps, when you merge, each node kind of alternates. You merge into the left, and then you merge into the right, and then you merge into the left, and then you merge into the right. And there's a couple ways you could look at that process. You could have a preferred child pointer that kind of toggles back and forth, that tells you which child you merge into, but you don't actually need to augment a node with a pointer to its preferred child. You can just swap your two children and always merge right. That's actually how this is implemented is you always merge right and then you swap your two kids, and that's effectively toggling between the two kids when you do the merging with the skew heap. The interesting thing though is when you read the skew heap paper, they actually describe the merge iteratively, not recursively. This is the recursive way of looking at this process. What's the iterative way of looking at this process? Of always merging right and then swapping. So actually the skew heap, the original skew heap paper, it seems to be kind of coming at the skew heap from the leftist heap idea. So the skew heap, another way to think about what happens with a skew heap is you always merge along the right spines. So the skew heap merge looks like this. It's just then after the merge, you walk up the right spine of the merged tree, and as opposed to the null path case where you would only swap if you need to, because you need to make sure that the right has the smaller null path, the skew heap just always swaps. So that's another way to think about how the skew heap works, is basically it's a leftist heap where you just, after you do a merge, you walk up the right spine of the resulting tree, and you basically, for every single node, you just swap its kids. Even if and you don't have to augment with null path length, you just swap the kids, just do it. And that works, as we saw from the amortization. So it would appear that whoever invented the skew heap might have kind of started with the leftist heap as their first data structure and tried to relax this idea of maintaining strict null path lengths. They said, well, what if we just always swap the kids? And oh wow, that actually works. So it seems like there's some historical basis where this thing might have been the precursor to the skew heap. But I think nowadays, like the top-down recursive viewpoint is probably the cleanest way to think about all of these structures, right? But they're all just kind of variations on the theme, right? Okay, so we talked about skew heaps before. Skew heaps are kind of cool. Sometimes people call these structures self-adjusting data structures because whenever you do an update to the structure applies some sort of kind of a restructuring heuristic, like, oh, I'm just going to swap all these people. And it doesn't seem to do that according to a reason. Like, it's not trying to swap these two things to restore an invariant on null path lengths or sizes or whatever. It just swaps them. It just always swaps them. And magically, that leads to good amortized performance. Later on, we're going to talk about probably the coolest data structure in the universe, the splay tree, which also is one of these self-adjusting data structures where every time you access an element, you kind of rotate it to the root with this splay operation. Irrespective of whether that seems good or bad, you just always just do this, blindly follow this restructuring heuristic. You just always splay the thing to the root, or you always swap the children. And if you just always do this, even if it's not informed by null path lengths or sizes, magically the amortization still works out well. So these kind of self-adjusting data structures are very, very cool and very mysterious and magical almost. That they work even though they're kind of blindly doing an operation, even if that operation is not informed by the need to like balance your two subtree sizes or change the left versus right according to null path lengths. Okay. Now, a while back, we had talked about, let me go back to the recursive outlook. Merging effectively boils down to choosing left versus right. And one of the ideas that came out last time was, why don't we just flip a coin? Right? That seems like even easier than any other operation. Maybe the skew heap is equally easy, right? The skew heap is just always merge right and then swap your kids. So that's like 2 lines of code. Another way you can do it is just flip a coin and 50% of the time merge left and 50% of the time merge right. So again, we don't need to augment our structure with anything. We just roll the dice and hope that we merge into the correct subtree. Now, do you guys think that that will lead to good performance? What does that kind of, if you think about that process from a null path perspective, how are you constructing your null paths? I start at the root, and how do I build a null path? Flip a coin, and if it's heads, I go left, if it's tails, I go right. So that process kind of corresponds to just randomly walking down a tree to discover a null path. Is that going to be a good null path or a bad null path? What do you think?
Half the time you'll
Statistically?
select the right option.
Yeah, like one of your children is good. It has like the smaller size. And if you flip your coin, there's a 50% chance at every step that you step to the good kid. So it kind of feels like, you know, odds are decent that you're going to make pretty good progress over time. I mean, what are the odds that every single coin flip is the bad coin flip, right? In other words, if I'm in a tree and I flip a coin and go left or right based on the coin flip, how long do you expect to walk before you fall off the bottom of the tree? You know, is that logarithmic? If it is, we're good, all right? And it turns out we're good, all right? So it turns out that that process of flipping a coin to walk down a tree, which is analogous to just flipping a coin to see if you want to merge left or right, that generates a null path of length log n with very high probability, okay? So let's prove that, and as part of that, it gives us an excuse to introduce some very, very helpful tools for analyzing randomized algorithms. Okay. So the first thing is, if I talk about something happening with high probability, I need to tell you what do I mean by with high probability, right? I've written software for a nuclear power plant, and I tell the operator, don't worry, this will run correctly with high probability. And they will look at you and say, what do you mean with high probability, right? This is a nuclear power plant, it should generally always work. So if you are responsible, you guys are a committee responsible for defining what with high probability should mean for algorithm design, right? People design randomized algorithms. A lot of algorithms, you know, they might work with high probability, or they might be efficient with high probability. How should we define this notion of with high probability? Like for example, if I want to say the running time is order log n with high probability, that means the running time is bounded by a constant times log n with high probability. What that should kind of mean is that the probability that we fail, the probability that we're not bounded by a constant times log n, the probability the running time is bigger than some constant times log n, that should be less than some very, very small value, right? There should be some very small failure probability where we fail to be bounded by a constant times log n. But how small should that failure probability be? What's a good way to kind of universally define with high probability that everyone in the world will be happy with?
Maybe like with the size of the problem.
That's the way to go, because you can't just say 1%, and then you know some people, the nuclear power plant is going to want 0.0001%. For other applications, I might be okay with 0.01%. You know, there's no universal constant that everyone in the world would agree on here. So, you know, just to be silly, you know, what constant are you comfortable with, right? So the probability you're struck by lightning in any given year is some very small amount. Would you be confident if your failure probability for your algorithm was that? I don't know, some other events that are not so likely. The probability of being bitten by a shark in a year is even less. The probability that you're hit by a meteor is 10 to the minus 10. So my concept of what I'm comfortable with is, I call this lightning, meteor, shark safety. I'm waiting for this to become an official ISO standard. But 10 to the minus 23rd, assuming there's no dependencies between these. So don't like go swimming in the middle of a meteor shower and a lightning storm or something like that. But so you know, I could say that 10 to the minus 23rd is a pretty safe value there, right? The probability that you're bitten by a shark and hit by lightning and struck by a meteor all in the same year. However, some people might not even be comfortable with that number. So putting any constant here seems to be, you know, there's just no mathematically motivated way to do that, you know, because why choose any constant over any other constant? So what we have to do is we actually pick a bound here that scales with the size of the problem, and that kind of makes sense. So what I'm going to use here is kind of an inverse polynomial bound. So the probability of failure that we're not bounded by k log n in terms of running time is at most 1 over our problem size to a constant, like 1 over n squared, 1 over n to the 100. It turns out actually this constant will be kind of something we can arbitrarily set. If we can set it to 2, we can set it to 3, and we can set it to 4 by choosing the hidden constant and the running time appropriately. So it turns out that what this constant is doesn't really matter. It's just that the form of this thing is 1 over a polynomial, right? So this is interesting because the bigger our problem gets, the better this guarantee gets, right? The probability of failure actually gets smaller and smaller in a dramatic fashion as the problem size gets larger and larger. And that's actually kind of, that makes sense, because if I'm solving a problem of size 3, like there's only 3 input elements using a randomized algorithm, there's only like a certain number of scenarios that can happen with my algorithm. There's only 3 inputs. So if you look at every possible execution trace of my algorithm, if only one of those fails, that's going to happen with pretty high probability, right? So a small instance kind of inherently has to have a high probability of failure, just because there's not much that can happen when your randomization plays out. Maybe there's 10 things that can happen randomly when you run your algorithm. If only one of them is bad, you've already got a 0.1 probability of failure. So you can't really make a strong guarantee for small input sizes. It's just not possible, because there's just only so many things randomization can do. But with large instances, you actually do have the ability to make stronger guarantees. And what this does is it kind of reflects the same thing that we wanted with big O notation. We care about the long term. We care about how the problem size scales asymptotically for large values of n. This is kind of the same idea. What we care about is the fact that this bound becomes strong for large values of n. So that as the problem size gets bigger and bigger and bigger, the probability that we fail to do whatever we want, the probability that we produce the wrong output, or the probability that we run in too much time, that drops off really fast. As an inverse polynomial, or you could even have something stronger than this. You could have like a negative exponential, like 2 to the minus n or something, would be even better. However, it turns out that 2 to the minus n is a little too much to hope for with most algorithms. With most randomized algorithms, this is the best you can prove. And so this has kind of become a standard idea in randomized algorithms. If someone says that this bound holds with high probability, what they mean is, and there's actually kind of a consensus that should mean that the probability of failure is 1 over a polynomial, 1 over n to a constant, kind of. I'll give you an example to show you how that happens and why the constant really doesn't matter. Okay. So basically, we run in order log n time with high probability if this holds. For any constant, basically any constant that we want C, we can find a constant K for which this statement is true. Right? Let me give you an example of how that works. All right, so this is something we commonly do with randomized algorithms. It's called boosting. The idea is you have an algorithm that's a randomized algorithm that looks pretty bad. So it has a failure probability that's slightly less than 1/2, but maybe not much less than 1/2. So you run the algorithm and it works with probability 2/3 and it fails with probability 1/3 maybe. That's not a very attractive algorithm, right? You don't want an algorithm that fails 1/3 of the time. However, if you have this algorithm and you have a mechanism for detecting failure, what can you then do with the algorithm? Just keep running it over and over and over again. Run it. If it fails, run it again. If it fails, run it again. Keep running it until you succeed. And each time there's at least a 1/2 chance of success, or at most a 1/2 chance of failure.
How do you know when you fail?
Well, it's an assumption that we can detect failure. If we can't detect failure, then we're toast. So if we can detect failure, though, you can just keep running the algorithm. This is something we do a lot with randomized algorithms. To boost the success probability, run it a bunch of times. And like if one of those times succeeds, you're good. The only way you fail is if all of them fail. All right? So if I run k iterations of my algorithm, and let's say k is some constant times log n, what's the probability of failure now? If I run the algorithm k times, I fail in aggregate only if every single one of those k iterations fails, right? If one of them succeeds, I'm done. So what's my new probability of failure? I guess it's on my slide, right? The probability of failure on any given run is 1/2. If I run k independent runs, those 1/2s all multiply together. The probability you fail after k iterations is the probability you fail in the first iteration times the probability you fail in the second iteration times the probability you fail in the third iteration, 1/2 times 1/2 times 1/2 times 1/2. So you can actually boost, or I guess decrease, the failure probability dramatically, right? You run k iterations, now your probability of failure is 1/2 to the k. And if we set k equals to a constant times log n, so we're going to basically run this thing for a logarithmic number of iterations, where n is like our problem size, then what's this bound look like? It's 1 over, this is actually convenient, 1/2 to the c log n. Right, it's 1/2 to the k, where k was a constant times log n. What's that equal to? 1/n(c). So if you want to have a failure probability of, I don't know, 1/n to the 100, like a really, really strong failure probability, 1/n to the 100. Everyone would be probably good with that, right? If your failure probability drops off like at a rate of 1/n to the 100, then you can achieve that by setting c to 100, which means you need to run this thing for 100 log n times. conveniently 100 is a constant, so that's still order of log n times. So whatever constant you want here, you can have by just setting the hidden constant in your running time appropriately. That's kind of the only weird thing about this definition is that you can actually set this constant to whatever you want it to be by tuning the constant in your order of log n running time, right? Whatever this constant is, it kind of affects whatever that constant is. So with high probability means you can get a bound of kind of 1 over c to some arbitrarily choosable constant by tuning the hidden constant in the running time. All right, so that's kind of the simplest example I can give you of how you get a high probability running time. Now you might think that proving like something complicated like merging two heaps together, how would we do that? How do we show that that happens in log n time with high probability? It turns out that that's really easy using a tool that I've actually developed myself and then published recently. So here's how I want you to think about it. This is a notion that's very comfortable and well understood by just about every algorithm designer. You teach it as to undergrads very easily. You start with the problem size n. If every step of your algorithm effectively decreases the problem size by a constant fraction, like to n to n over 2 to n over 4, then you take a logarithmic number of iterations, right? So anytime you have kind of a multiplicative reduction in problem size at every step, that leads you to a logarithmic number of iterations. Binary search is probably the simplest prototypical example, right? You're searching an array of size n. You look at the middle element and decide, do I go one way or the other? And then after that one step, you have effectively a size n over 2 problem to search. So every single time, if every step of your algorithm reduces the effective size of the problem by a constant fraction, then you take order log n iterations, right? This is kind of, call this the reduction lemma, maybe, right? It's a very easy, this is an easy concept, right? Makes sense. So one of the things that I've been teaching in my classes, and I've now actually published a paper on the idea, because I think that it really helps simplify the design of a lot of randomized algorithms, is just taking that concept one little step further to what we call the randomized reduction lemma. So it turns out that your algorithm has a log n running time, an order log n running time with high probability if it does something very similar. Instead of always reducing the problem size by a constant fraction in each step, it has a constant probability of reducing the problem size by a constant fraction in each step. So maybe it reduces the problem size by half with 2/3 probability at each step. So there's at least some constant probability of a constant size reduction at each step of the algorithm. If that's the case, then you take only order log n iterations with high probability, and kind of intuitively that makes sense. This is, go back to the null path example. One of your two children is good, right? It has less than half the size of the whole tree. So every step I take, when I flip a coin and go left or right, there's a 1/2 chance I land on the good subtree that has less than half the mass of the original tree. So every single step, if I'm finding a random null path down a tree, there's a 1/2 probability that I take a step that will reduce my tree size to half of what it used to be. All right, so that satisfies the conditions of the randomized reduction lemma, which means that I take only order log n iterations of high probability. Hidden behind this is some really fun probability Chernoff bounds and random variables and things that we'll get to maybe in about 3 or 4 weeks. And then you will thank me that we have this really simple kind of idea of the randomized reduction lemma, because without this, you have to take about 3 or 4 more lectures to learn about maybe 5 or 6 kind of tools and probability theory before you can actually make this sort of statement. And the amount of mathematics you have to do is about 3 pages. Whereas here it's just every step you reduce the effective problem size by some constant fraction with some constant probability, and that guarantees an order log n running time with high probability. All right. I'll post the paper we published on this. I'll post it on Canvas. What we did with this paper is we showed that maybe about 24 common algorithms and data structures, you can take their analysis from 3 pages down to a paragraph using this tool. So it really helps you clean up a lot of randomized algorithms. We'll be able to analyze randomized quicksort in about 2 sentences with this thing. So it really helps. Okay, so let's just do an example to see how easy this is. Regular binary search, right? With regular binary search, you've got an array, you're trying to find an element. This satisfies the reduction lemma, because after every step, you look at the middle element and you either go left or right, and so after each step, you're either effectively searching only the first half or only the second half of the array. So each step halves the size of the array under consideration. What if we, instead of doing binary search, we do randomized binary search? What's randomized binary search? I've got a sorted array and I'm searching. I don't compare to the middle element. Who do I compare to?
Any element.
Any element.
Yeah.
That's kind of what you do in practice, right? If you're looking somebody up in the phone book. Way back when, 10 years ago, there were these things called phone books, right? They were alphabetized, maybe a dictionary, right? A paper dictionary. They still make those. If I'm trying to search for a word in a dictionary, I don't have the dexterity to open it to the exact middle word, right? By the way, what is the middle word in the dictionary? I looked it up once as a janitor. So I don't have the I don't have the physical ability to open to the exact middle page. So when I do a binary search, I do a randomized I just open the book to some word. So I compare against that word, and then I either recurse on the left or the right appropriately. That still works, but what's the running time? It kind of seems like it should be log n-ish, right? Because you're still kind of making pretty good progress. You're just not always exactly having things. And it turns out that you can use the randomized reduction lemma to show that. So here's how. Here's the sorted array that you're searching. Let's kind of mentally divide it up into 3 sections of size n over 3. If I so happen, and remember what I do is I pick a random element to compare against. There's a 1/3 chance that I'm lucky enough and I pick that random element in the middle third. If that's the case, if I pick my random element to compare against in the middle third, then no matter what, if I go left or right, I'm losing 1/3 of the mass of my problem. Like if I recurse to the left, everything in the last third goes away, and my subproblem only contains things that were in the first 2/3. If I recurse to the right, then everything in the first third kind of effectively evaporates and goes away, and now my subproblem remaining only has elements that come from the last 2/3 here. So every step, there's at least a 1/3 chance, like if I pick someone from the middle third, that my leftover subproblem will have size at most 2/3 of its original. And so these two things are constants. There's a constant probability of reducing by a constant fraction in each step, so I can just use the randomized reduction lemma to say this takes order log n steps with high probability. Okay. Now usually there's a question after this slide of why can't I get 1/2 and 1/2 here? I'll let you guys think about that. That's a little too strong to prove, all right? It's a lot to insist that the problem size reduces by 1/2, because for that you have to actually pick the exact middle element, and there's a very low probability of doing that. So this is a little more relaxed to give good constant bounds. You could have made slightly different arguments and gotten slightly different constants, and that works fine. All right, but 1/2, 1/2 is a little too aggressive to get. So this is kind of a prototypical use of randomized reduction. Another example is for mergeable heaps. In each step, if you're taking a random null path, with probability 1/2, you step to the good child, and so you reduce the number of nodes in your current subtree by a factor of at least 2. And you're done, right? Because now how long is a random null path? It's order log n with high probability. Yeah.
So is it kind of like recursion, except for randomized?
Basically, so anytime you have an algorithm that's recursive, as long as you can show that at each step, as long as there's a constant probability that it kind of recurses on a subproblem of only a fraction of the size, you're done. And it has to be like a constant fraction of the size, like n over 2 or 2/3 that. It can't be n minus 1. It has to be a multiplicatively smaller constant. Okay. But so we can actually, this one tool, randomized reduction, it simplifies this dramatically, and many other randomized algorithms. Let me give you another example. Also related to heaps, why not? We build an n-element binary heap. One way to do that is just insert n elements, insert, insert, insert. Every time you insert an element, it kind of gets put at the bottom of the heap and sifted up. And if you're kind of unlucky, what's the worst case of that? Like everything gets sifted all the way up to the top of the heap and it takes n log n time. So what order would you have to insert in to realize that worst case?
Like sorted.
Sorted, increasing or decreasing sorted order?
Well, you have the minimum at the top.
The minimum's at the top, yeah.
So decreasing.
So decreasing, right? So if you insert things in descending order, every element is now the new minimum and gets pulled all the way up to the top of the heap with sift up. And so every element takes log n time to insert. That's the worst case. So maybe we can mitigate that by inserting things not just in whatever order your adversary gives them to you, but just insert them in random order. All right? Does that help? Can that avoid the worst case? It seems very unlikely that if you insert n elements in random order, that they're going to end up in descending order. Right? That doesn't seem very likely. And it turns out that if you do this, the running time drops from n log n to linear in expectation, kind of. So this does help. In fact, you can even show linear with high probability, I think. But let's look at a simple case. How many times do we change the root during this process? I don't care about the whole running time, but just the root. So I'm inserting elements one by one. What has to be true of the element that I just inserted if it gets pulled all the way up to the root? Yeah, it's like the new minimum, right? So another way to ask this same problem is, if I scan through a random permutation of n elements, like the order that I insert, how many times will you see the minimum be reset? How many times will you see an element that is the new minimum over the whole array?
Log in with high probability?
Yes.
Okay.
But why? Right? This is actually a very common algorithmic process. You can find like 12 algorithms where this is kind of what you need to solve to analyze it. You know, I'm like inserting things in random order, and something bad happens if the thing I'm inserting is the new minimum. So how many times does do you hit a new running minimum? How many times does a running minimum get reset if you randomly permute n things? The answer is, of course, log in with high probability, because we're trying to illustrate randomized reduction. But how do we phrase this in a way that lets us apply randomized reduction? Remember, randomized reduction, we have to have some sort of process where at every step there's a constant fraction that our problem size decreases by a constant fraction. And that doesn't seem obvious from this, how we get that phrasing. So let me look at our random permutation of size n. Here's 3, 1, 4, 2, 6, 7, 0, and so on. And let me basically mark all the times, if I'm scanning through this thing, mark all the times where I see a new minimum. All right, so I'm going to put a check mark over every element that is the smallest element up to that point. So I'm keeping a running minimum, put a check mark every time that gets reset. How many check marks? That's what I'm asking.
Oh, just the first element.
Well, the first element is always checked, and then whoever dethrones the first element is the next check mark, and so on. I claim there's order log n check marks with high probability. All right. Here's my reasoning. Let me put just for simplicity, I'm going to put a minus infinity at the end of my array. So I know that's the last check mark. All right. This is just to avoid special cases and whatnot. So let's start here at this last check mark. Where's the previous check mark? Where's the,
right
if I want
next
to
to
step
it?
backwards, I know I start at this last guy. He's the last check mark. Where's the one right before it? This is a random permutation. So it's whatever the smallest element is in this.
The true minimum.
So let me cut this in half. What's the probability that previous check mark is in this half versus this half? 1/2 on each side, right? So there's a 1/2 chance that it's somewhere here. And that's good news, because if I step backward from this check mark to the preceding check mark, I've effectively halved the size of the, I start at my index here, n+1, drops to an index that is less than half of what it used to be. And so every step of the process actually has this exact kind of feel to it. If I step from each check mark to the check mark before me, there's a 1/2 chance that that preceding check mark lives in the first half versus the second half of all the elements before me. So my index effectively halves at each step with 1/2 probability. And so according to that, I run out of check marks in order to log n steps with high probability. Okay, so sometimes it takes a little bit of cleverness in how you phrase the argument, but you can actually take things that don't look like they fit the randomized reduction lemma and articulate them in a way that satisfies those conditions very easily. Proving this without randomized reduction can be a little bit more of an interesting exercise in probability theory. All right, so there's a lot of problems where this process is kind of, once you see the setup, it's like, oh, that's pretty cool. There's a 1/2 chance that your index drops by a factor of 4.5. So I'll post the paper so you can see a couple more examples where that sort of thing happens. But this is our first randomized algorithm analysis. Alright, we'll see you guys on Tuesday.